We're back with section 6.3. We're in part two of this. We're going to use differential equations to model and solve applied problems. Now, I'm going to split this into two videos because I have several examples I want to go over. So, the rate of change of the number of coyotes, N of t, in a population is directly proportional to 650 minus N of t, where t is the time in years. When t equals 0, the population is 300. When t equals 2, the population has increased to 500. Find the population when t is 3, and then we're going to go ahead and graph that solution. So, we have the differential equation dn dt equals k times 650 minus n because it's directly proportional and it's the rate of change. So dn dt equals k times 650 minus n. We can solve this by separation of variables. So we would have dn over 650 minus n equals k dt. And then we could integrate each side. The right side is with respect to t, and k is understood to be a constant, so that would be kt plus c. The left side is natural log. But you would have a negative in there because the denominator is 650 minus n, so negative natural log, absolute value 650 minus n. It is helpful to multiply both sides by 1 or negative 1. And since 650 is the population capacity, we don't need the absolute value. So this would be negative kt plus c. All right, and then we exponentiate both sides. You would have 650 minus n equals c e to the negative kt. Remember, when you add in the exponents, you can multiply like bases. So it's e to the c, which we can rewrite as a constant. So this gives us our general solution n equals 650 minus e to the negative kt. Also, we know that the population is 300 when t is 0. So 300 equals 650 minus 1. So that's going to give us, when we plug in 0, we get 650 minus 1. I forgot the c there, that's why. So minus c, so c is equal to 650 minus 300, which is 350. So n is equal to 650 minus 350 e to the negative kt. Now we have to use the other information they've given us to find the value of k. The other piece of information is when t is 2, the population is 500. So 500 equals 650 minus 350 e to the negative k times 2. If we subtract 650 and then divide by 350, we would end up with 3/7 equals e to the negative 2k. We natural log both sides and divide by negative 2. Then you would have k is approximately 0.4236. So we have n of t equals 650 minus 350 e to the negative 0.4236 t. So when t equals 3, you would have 650 minus 350 e to the negative 0.4236 times 3. And that's going to come out to approximately 522 coyotes. So we're going to look at a model of this population in Desmos. Here we have the graph of N of t. It's in purple here, and you can see that the graph is increasing and concave down. I graphed 650, which is the limiting value of this function as t approaches infinity. We could see that the graph kind of levels off there. We're going to go ahead and move on to the next example. But before we do, we have to note that n equals 350 is, it's actually 650, that's just a little typo there, is the horizontal asymptote of the graph and represents the carrying capacity of the model. We'll talk more about this in the next section. A common problem deals with electrostatics, thermodynamics, and hydrodynamics and involves finding a family of curves, each of which is what we say orthogonal to all members of a given family of curves. So for example, a family of circles, x squared plus y squared equals c squared, each of which intersects the lines in the family y equals kx at right angles. Two such families of curves are said to be mutually orthogonal, and each curve in one family of the families is called an orthogonal trajectory of the other family. In electrostatics, lines of force are orthogonal to the equipotential curves. In thermodynamics, the flow of heat across a plane surface is orthogonal to the isothermal curves, and so forth and so on. In this graph below, each line is an orthogonal trajectory of the family of circles. Basically, this is a complicated way of saying these lines all intersect the circles at right angles. So in example 5 here, we're going to find the equations of the orthogonal trajectories for the family of curves given by y equals c over x, where c is not equal to 0, and then we're going to use Desmos to draw those. So the first thing we want to do is write this equation as xy equals c, and then by differentiating implicitly with respect to x, we would have x dy dx equals, or plus y equals 0. Then we could separate this equation and we would have, or excuse me, we could solve for dy dx and we would have negative y over x. Now here's the important part. Because this equation represents the slope of the given family at any point, it follows that the orthogonal family, which intersects the curve at right angles, is going to be the opposite reciprocal. In other words, perpendicular. So the orthogonal slopes, dy dx, are going to be x over y, positive x over y. Then this is what we can solve. So multiply both sides by y and dx, separate those, integrate, so you have 1/2 y squared equals 1/2 x squared plus c. And then we can multiply both sides by 2 and subtract the x squared. You have y squared minus x squared equals, we'll call it k. And k just represents what you would get for the constant after you solve the equation like this. So the orthogonal trajectories for the family of curves given by our original equation, y equals c over x, is the family of curves given by the equation y squared minus x squared equals k. So what we want to do is go ahead and graph these in Desmos to get a picture of what they look like. So we'll bring that up. So what I did was I graphed the original curve y equals c over x, and I created this list of numbers. And what it does is it's just telling Desmos to graph the equation y equals c over x for these 8 values of c, and those are going to be the curves that are in blue. Then I entered the equation for the orthogonal trajectory and then told it to graph it for k values -4 through 4. Now I didn't include any values where k is equal to 0 or c equal to 0, because then that was the constraint from the beginning of the problem. So we can see some things that happen here. So namely, when k is greater than 0, so let's look, I put in like 4 or 3 or 2 or 1 or even 10, and so forth and so on. The transverse axes are vertical. And if the k value is negative, so like -4, -3, uh, -2, -1. The transverse axes are going to be horizontal. And the orthogonal trajectories are the lines y equals plus or minus x if I included 0 in this list here and 0 in this list here. We would have the horizontal line there. Okie doke. For our next example, a new cereal product is introduced through an advertising campaign to a population of 1 million potential customers. The rate at which the population hears about the product is assumed to be proportional to the number of people who are not yet aware of the product. By the end of 1 year, half of the population has heard of the product. How many will have heard of it by the end of 2 years? We can also graph this solution in Desmos when we're done here. So this problem says the rate of change, so dy dt, is proportional to the difference between 1 and y. So proportional to the difference between 1 and y. Because it's proportional to the number of people who are not yet aware of the product. So if y is the number of people at time t who haven't heard of it, that means 1 minus y is the number of people who have not heard of it if y is considered to be in millions. So instead of writing 1 million minus y, just writing 1 minus y and understanding that y represents the number of people in millions. Now, we can separate this, so dy over 1 minus y equals k dt. We're going to integrate both sides, and you would have negative natural log absolute value 1 minus y equals kt plus c. We're going to divide off that negative to eliminate that issue right there. So negative kt. And I'm still going to write plus c because whether you add or subtract a constant, you're still adding or subtracting a constant. Exponentiate both sides. You'd have 1 minus y equals e to the negative kt plus c. And I also took off the absolute values because we're assuming that y is going to be less than 1. Because remember, y represents millions of people. If there's 1 million potential customers, then y is not going to get bigger than 1. So if we solve this for y, we would have y equals 1 minus capital C e to the negative kt. And all I did there was remember when you multiply in the exponent here, or excuse me, add in the exponent here, it's like multiplying like bases. So this gives us our general solution. So to solve for the constants c and k, we would have to use the initial conditions. And because when y is equal to 0, when t is equal to 0, because remember, y represents the number of people in millions who have heard of the product. So when I plug that in, I'm going to get c equals 1. Similarly, y is going to be equal to half, so 0.5, when t equals 1. So this means that 0.5 equals 1 minus 1 e to the negative k. So all I'm doing is putting c equals 1 in for c, and then substituting 0.5 and 1 in for t. Now, when I solve this equation, you would subtract the 1, divide by the -1, natural log both sides, solve for k. You'd end up with k equals natural log of 2, which is approximately equal to 0.693. So the particular solution to our situation is y equals 1 minus e to the negative 0.693 t. That's the particular solution. And we want to know how many will have heard of it at the end of 2 years. If we plug in 2, you will get about 0.75, which remember that's 0.75 million people, which is 750,000 people. Okay, extra comma in there. All right, if we would graph this situation in Desmos, I'll pull that up in just a second. So here we have the graph of y. I plotted the 0.2, comma 0.75. Notice also that you can determine that the number of people, well, basically we have after 2 years, 0.75 or 750,000 people have heard of the product. Notice that the horizontal asymptote for this graph is at y equals 1, which is the maximum population here of 1,000 potential customers. All right, guys, that's it for this video.